All right, thank you for coming. My name is Sujit Paul. I work for Elsevier Labs. And today I'm going to talk about this 4-step recipe for text classification and similarity. Essentially, you can think of these as Lego blocks. So it's embed, encode, attend, predict, and you can rearrange these Lego blocks in various ways, right? So the inspiration for this talk is this blog post by Matthew Honnibal. Matthew Honnibal is the creator of SpaCy, the deep learning toolkit for Python. This is quite recent now. He wrote it about 6 months ago, and some of it is kind of outdated at the moment because deep learning moves so fast. But in general, the advice and the actual ideas are very much valid, and I think it can be very useful for us to kind of follow it. So before I start, I want to acknowledge the people who, the code that made it possible. Keras for the deep learning part. I used NLTK for most of the natural language processing part. I couldn't find a logo for it, so the best I could come up with is a book. And scikit-learn for some of its metrics, some of its transformers as well. But most of it is, scikit-learn was kind of used on the side, right, to give functionality that I needed. So I'm going to just set up a little agenda, like what we're going to cover. Just to set the stage, I'm going to talk a little bit about NLP pipelines before deep learning. If any of you went to Alexander Jones' tutorial yesterday, he covered this whole thing in a lot more depth than I'm going to. But it's basically, it's kind of setting the stage, right? The second part is basically I take each of these steps and deconstruct them, kind of explain what they are and so forth. And then I talk about 3 examples that I did. One for using document classification, and one for using document similarity, and one for using sentence similarity. So NLP pipelines before deep learning. Essentially, most of the NLP that we see before deep learning started from information retrieval, right, based on requirements for search engines. So essentially what you had was you had this corpus of text, and you would tokenize it, and you create a term document matrix, right? So documents down the rows, terms down the columns, right, across the columns. And you would say that anywhere where the term occurred, you add a 1. So it becomes a really large sparse matrix with the numbers, the counts in that matrix. And then you could apply some transformations such as maybe TF-IDF, and you come up with a TF-IDF term document matrix. If you wanted, it's still very sparse because the across part is still the size of the vocabulary you're talking about. If you wanted to densify it, you would maybe use LDA or SVD to do feature reduction or topic modeling. And you would end up with a topic document matrix, right? Less topics on the columns, but same number of documents. And the object of this whole thing is to mainly feed it into something like an SVM, a support vector machine for document classification or something like that. Another kind of related approach is from the machine learning side of the house. So machine learning has a recipe of how to deal with categorical variables that you turn it into a one-hot vector. So if you think of a text as basically a bunch of words, and each word being a categorical variable, essentially you're talking about a large category space, which is equal to the size of the vocabulary, right? And within that, each word occupies exactly one position, right? So that's another way to look at it. And again, the pipeline is kind of similar, except that once you tokenize, you create a vocabulary, right? You create words and you create IDs for it. And then you could take something, like this: a man is riding a bicycle, right? This is my sentence. It's basically a string of words. It's a sequence of words. And using this vocabulary where you can look up a word and get an ID, you can reduce it to a sequence of numbers, sequence of integers. And then, using the sequence of integers, you can now create your term document matrix. But this is slightly different, not exactly the same, but it's still a term document matrix, right? The problem with this is that this kind of one-hot encoding does not have distributional semantics at the word level. What do I mean by distributional semantics? So if you look at the sentence again and instead say, a man is riding a motorcycle, right? Typically you would think the bicycle and motorcycle are similar. But if you take the word vectors and you do a cosine similarity, you'll get 0 because they have ones at different places, right? So at the word level, there is no concept of meaning in the word vectors, in one-hot vectors. So the next step comes up is word embeddings, and word embeddings kind of have this thing where the words kind of inherit their meaning, right, based on how it occurs. So essentially, a word embedding kind of create similar vectors if they occur in similar contexts, right? So in a sense, they kind of encode the meaning of the word. So there are various flavors. The nice thing about word embeddings today is that there's a bunch of them available for free and trained on large corpora. So one of them is word2vec. So there are two flavors of word2vec: CBOW, where you predict the word from the context, and skipgram, where you go the other direction. Skipgram is generally more popular, and the image here shows you basically the skipgram, how it's actually set up. Essentially, it's a classification task, and except that it's on unsupervised data. You're depending on the structure of language to give you the structure, right? So what you're doing is you slide a moving window across your sentences, and you take that word as the input and the neighbors as the outputs, right? So essentially what you're doing here is you're sending in a one-hot vector for, say in the second case, right? You're sending a one-hot vector for man, and you're sending it through this autoencoder kind of thing where you kind of condense it to a hidden state, which is the size of the embedding you want. And then you again expand it out to the size of the vocabulary. And you're trying to train this network so it can predict, in this case, A and is, right? So you send in man, it should predict is. You send in man, it should predict A, right? Once you have something that is reasonably trained, you can now extract the weights from here, and that's your embedding, right? So you have your vocabulary to embedding, right? So each row would be a vocabulary, and the actual row for that is the word embedding for that word. Glove is kind of different. Glove, you start off with this whole vocabulary in advance. You do a word to context kind of co-occurrence matrix first, and then you factorize the matrix to create a word to embedding and hidden to context, right? So, and you take the left-hand side once you are trained. Fast text is similar to word2vec, except it works on subwords, which makes it much better. Basically, trigrams or pentagrams of characters instead of actually full words. So that's word embeddings. So now that we know about word embeddings, let's talk about the first the step in the 4-step recipe. The embed step, right? So here we are using, so if you look at this diagram, you'll see it's almost the same as the one 2 slides ago. The only difference is that we have replaced the one-hot vector that we generated with the pre-trained vector that we got from one of these third-party embeddings, right? So essentially you do the exact same thing. You create your vocabulary, and then you look up your sentence. You convert your sentence to a string of ints. And the embed step basically does, it takes an int, it creates a vector, right? And so the idea is that, and since a sentence is a sequence of ints, essentially you end up with a sequence of word vectors, which is basically a matrix, right? So you could think of a sentence as being a matrix. The second step is encode. And so encode takes, again, we kind of we covered a little bit from the previous one, where you take a sequence of vectors and you convert it into some kind of matrix, right? So the naive way is to basically concatenate all these vectors on the short side and create this matrix, right? But the encode step here talks about slightly different. It says that, okay, you want to encode it such that the meaning of each word in the context of the sentence is retained, right? So let's say you had, in a 5-word sentence, you had 2 words which were really indicative of the meaning. You want that to have more impact, right, in the final matrix that you get. So that's what this does, and typically you do it with a bidirectional LSTM or a bidirectional group. So LSTM is long short-term memory, and GRU is a gated recurrent unit. These are drop-in replacements for recurrent neural network cells. And usually you can get this like third-party. I used Keras, and Keras has layers which have LSTM functionality built in, so you don't actually have to think about what's going on inside. And the reason for bidirectional is basically because you want words at the beginning to have the same impact as the words at the end, right? So you read one left to right, one right to left, and you concatenate or add them or something. So that way you get, all the words get equal impact. The next step is attend. Basically, attend is you just got a sentence matrix in my previous step, right? Now you want to reduce it to a vector. And again, the naive way to reduce it to a vector is maybe do a max pool or do an average pool, right? So essentially, you look at this vector and you say, okay, I want to find the maximum here, of each column, and I create this little row. So that's my max pooled vector. Or I just add them up and average them. Again, that's the average pool thing. But again, we don't want to do something naive. We want to basically have another layer which basically kind of tries to minimize the information loss from the matrix to the vector, right? So you want to do something smart. And actually, I spent quite a lot of time trying to figure out what thing to do and reading papers and so forth. So I'll actually cover that in quite a bit of depth. And so from the blog post, there are basically, they talk about two types of attention mechanisms. One that takes a matrix and a vector and creates a vector, and one that takes two matrices and creates a vector. And while I was researching, there was a third and a fourth one that I kind of found, where you take a matrix by itself and you try to reduce it to a vector, no additional vectors. And there is another one where you take a matrix and in the process of reducing it to a vector, you actually learn another vector, which is called the context vector, right? So I'm going to cover those in a little bit of detail, only because, especially if you work with Keras, all the other steps, they actually have layers already available, right? Attention is the only one which is kind of non-standard, and that's probably why they don't have the layers. So I had to build my own custom layers, which I'll also talk about. So it's not that really hard. So in any case, so I start with the first type of attention. There are 4 types. So in this case, if you look at this diagram to the right on the top, this is kind of the high-level view. You take a matrix, you pass it through attend, and you get a vector. The other view, which I find more useful, especially if you're trying to implement this thing, is the equations, right? And so essentially, and the diagram at this here is basically the equations in diagram form, right? So essentially what you get is from the output of the LSTM that you got, that's H, and you have 2 weight vectors, or the weight vector W and a bias vector B, which you learn, right? And during the training process, where you have this entire NLP pipeline, and it's a training process, right? So you are trying to train the network. And during backpropagation, you start off with random values for the W and B. And during backpropagation, you would basically update it each time, right? And over time, once your network is trained, this W and B are now adapted to the task at hand. So essentially, attention is also learning, right? So that's something that eluded me for a long time, but then I kind of got it, so I just wanted to kind of share it with you guys. So essentially what you do is you take the input signal, H, you multiply it with a weight matrix and add a bias, and you take the tan H of that. So the tan H kind of squashes it between -1 and 1. And then you take that and you run a softmax on the remaining, on the output. So what softmax does is basically it creates, it again pushes it between, not pushes it, it makes it so that it adds up to 1. So essentially these are probabilities. So intuitively you can think of these, the alphas, as the probability of each word in your sentence, right? How much to weight them. And then the final step is you take the original signal and you dot product it with this alphas, and then you sum it over all time steps, and that's the vector you get, right? So this is proposed by a researcher called Raphael and his team. And I have references at the end, so you have the papers there, so you can just read it up yourself. As you can see, the intuition is basically to select the most important element from each time step, right? Essentially at each word. So you take the most important word there. And as I mentioned before, weights W and B are learnable, and it depends on the target. And I'm going to show you the code here. I'm not going to show you code for everything, mainly because it's kind of repetitive, and once you know one, you know the others. So essentially, this is the custom layer. So you can see here, I'm extending layer. And then there is a bit of boilerplate that you can find from the Keras custom layers page as well. So you need to add this. You need to call the superclass, right? So in your init, and you need to call the superclass in your build. And in your build, you basically set up these random, the weights that are going to be populated with random values. Here I have, the weight vector I'm initializing to normal values, and the bias vector I'm initializing to zeros. And you can see the shapes here and so forth. The shape is in terms of the input shape that I get. Similarly, the actual equations that we talked about are there in this call method, right? So it's essentially I'm using the Keras backend to implement these equations. And basically, it just follows the equations. If you look at the equations and you look at this, it's like a one-to-one correspondence. Okay. All right. Yes.
Why do you have two activations?
Why do I have three activations?
Two activations. Like why run TANH and then not max
The TANH is basically, so when your input comes in, you want to kind of squash it down, because otherwise the sizes get too large, the input signal sizes, and when you try to backpropagate, they explode, right? I actually found this and in a later one, and I ultimately ended up patching it with the batch normalization layer after this. So that kind of does the same thing, but yes.
What's your mathematical operation for an attend? Like, what do you exactly do?
Okay, so there are 4 kinds, right? So let's see here.
Could you repeat the question?
Yeah, sure. The question was, what are the mathematical operations that are used in attend, right? So, so this is the first set. So I talked about 4 different kinds of attention, right? I said there are 4 I found. And this is the first kind. This is the easiest one, right? So this is the normal thing with deep learning, they call it activation. This is not activation, this is attention. Activation is when you take, I'm sorry. The language of deep learning, that's what you call activation function in hyperbole. Yes, but in this case it is, well, yeah, TANH is also, yes, it's an activation function. It's just a different terminology. Not really, it's actually, the purpose is different. In case of when you're trying to do an activation, you're trying to squash your input into a certain range, right? And whereas here you are trying to take a signal and you're trying to, kind of attune it, almost like how you tune your radio, right? You get different signals coming in, and you just come to the right place where the weights are all canceled out, and you get the right signal. It's exactly that, right? So you're trying to learn something which is kind of maximizes your signal, right? So anyway, so this is the first kind of attention. I showed you code. The second kind, okay. This is still the first kind, okay. Yes. So the second kind is kind of similar to this, except there is one difference, right? As before, you have a matrix. You use an attention mechanism to create a vector. But in the process, you learn a context vector as well. And this context vector is used to further influence the output, right? And again, the equations, if you look at it, is very similar. The first equation is identical, right, to what you saw before. The second equation, however, is a little different. So now instead of, so you have this E that you just got out of the TANH, and now you're multiplying this learned context vector along with that, right? And then you're taking a softmax. So again, it's a little different, produces slightly different results, proposed by Lin here. So I just blindly copied their paper, so that's how they proposed. And the only thing I've done here is that they all had different notations, so I kind of normalized the notation for my own sanity, right? And so for presentation purposes. So this is how you do it. Again, as you can see, the U is the learned context vector, and that comes in, as a result of the learning itself, right? Third one is, again, this is, yeah. Sure.
So how the U was constructed?
The U is constructed as it is learned as a result of this whole thing. If you look at the second equation, right? So the whole point is that this is just a set of operations, right? As you go through the network forward, these are the operations that are executed, right? And as you go backwards, once you know the result, right? During training, you have labels, right? So the labels, you basically find the difference in what you predicted and the labels, and you calculate the gradient and you move the gradient backwards, right? Now, as you move the gradient backwards, all these functions are differentiated also, right? Because you want the gradients to propagate back. And as a result, and because you want to minimize the difference here, right? At the end, between the prediction and the labels, your weights keep changing. Right? It learns as a, the weights that you have, they are basically, they learn. You start with random weights, and they kind of converge to correct values. So essentially, this is another hyperparameter that you're tuning. Think about it in machine learning. That's exactly that it is, right?
But the U could be, a lot of degree of freedom, not degree of freedom. So I guess the U could be very differently in different, learning. Iteration or different days, right?
Yes, it can be. That's the whole idea, really. I mean, you are introducing another variable to make it learn better, where better is kind of by a definition, right? It depends on what you're trying to do, your task, right? So your task will determine what is better, right?
After you learn this vector, is there an interpretation of it?
The interpretation is basically, you can think of it as weights that try to maximize the information that you extract. Right. So essentially, if you think of, for instance, in terms of translation, right, between some language and some other language. So if you take a sentence in a source language and a sentence in a target language, you want to give most importance to the words in the source language which mean a lot in the target language, right? So that is basically the interpretation. It's basically reweighting the vector, right? So anyway, so the third one is kind of a variation on the same, the previous two. But instead of matrix, you get a matrix and a vector. The vector is provided by you, the user, right? And it could be the context vector. So if you had, an LSTM that created the matrix, right? You could take the last one because the last one is the final context as your vector. You could take a max pool of that and produce another vector. You could even, take another process itself could come up with another separate vector, and you could merge the two together. And essentially here you're taking these two, and you're sending it again. You're creating a vector. Equation-wise, the only difference is up in the where you create your the raw signal that is tanh. You basically add this new weight u and the context vector that you were given, right? And everything else is the same. And this was proposed by another researcher and his team called Cho and his team. And again, the intuition is here, it's kind of a variation of the same thing. It's select the most important element from each time step and weight it with the learned multiple for provided context vector. It just make it more and more complex, this sentence. But essentially, it's just reweighting the thing. Finally, we come to the most, okay. Finally, we come to the most complex one, the matrix to matrix. So you have two input matrices and it produces one vector. And basically so here you can think of this second matrix, or if you remember the previous one where it had one matrix and one provided context vector, right? So you can actually manufacture the context vector by constructing an alignment of the two matrices, right? If you do a similarity, if you do so in here, if you notice, the E on the left is a tanh, just as you saw before with the W and H. The E on the right is another tanh. But now you have these two matrices, and then you multiply them together, and you get a similarity matrix, right? Now, using the similarity matrix, you then take the softmax of the similarity matrix and you multiply it with the original signal, right? So if you look at the diagram here, it's easier to understand. So you take these two signals, combine them together, you get your similarity, alignment, and then you take this, the softmax of this, and you combine the original signal with the softmax of the other one, right? And similarly, this signal with the softmax of the other one. So this creates your context vectors for the other guy, right? And once you do that, you, again, do very similar things. You basically do a tan H of that, and you sum over all the time steps. And then once you're done, you concatenate the two, and you produce your bigger vector. So this is double the size. If you concatenate, you could do other things. You could do sum, div, whatever, right? The code for this is slightly more hairy, but again, it's just the init and the build again. It's not... it's all there in GitHub. The GitHub is there in the slides, and go ahead and look at it, and you'll actually, it's easier to read than talk about, I guess. The final step is the predict step. The predict step is basically, it takes a reduced vector that we just got out of my attention, and it creates a label, right? And to do that, it's just a basic fully connected network, right? So generally, you use a shallow, fully connected network. You could also, if you were looking to do regressions, for instance, say you wanted to do ranking of similarity or something like that, you could change this, the top, to instead of doing a softmax, and actually, you can get it, even if you do a softmax, you just get a bunch of probabilities, right? And then when you do classification, you choose the highest probability one. But once you get your bunch of probabilities, you could treat it as regression, right? So you could just treat it as scores. So you could use it as a regression thing as well. So this is basically the setup that, the 4 steps that we talked about. So first example, let's go into that. So my data set was the 20 newsgroups data set. I got it out of scikit-learn. They come prepackaged with it, so you can download it. It had 40,000 training records, 10,000 test records. They're just newsgroup postings, about maybe 4 or 5 sentences long, slightly longer sometimes. And the output is, the task here is to figure out what category they are in, and there are 20 categories. So output, number of classes is 20. So I tried various, subsets of this 4-step procedure. So my first step was embed and predict initially. So essentially, this is the bag of words idea. So I treat a sentence as a bag of words and a document as a bag of sentences, right? So what I do is I tokenize the text, and then I create my vocabulary. And for each word, I do my embedding. I use glove here as my third-party embedding. And then I get my glove word vector, right? And then, since a sentence is a bag of words, I basically add all the vectors, I create my sentence vector, and I average them again. And again, since my document is a bag of sentences, I take my sentence vectors, add them up, average them again. And then I send it through a fully connected layer, the predict layer, and basically get my prediction. So this is like really simple. This is how I used to do it before I learned how to do the other stuff. And I can show you the code for this. This is like really simple. Let's see. So most of it is pre-processing and getting it to fit the thing. Here is the network definition, and you can see a kind of a diagram for it. It's really simple, 2 layers with dropouts on both. I think dropouts in 1, or no, maybe 2. Yeah. So and then when I train it for, I think 10 epochs. I think 10 epochs, and I get an accuracy of 71% on my test set, right? So I basically train it on the 40,000. I test it on the remaining 10,000, and okay. And then, so this was my kind of my baseline. So it gives me like 71% or so. So the second one was where I actually do the embed, encode, and the predict, right? So I actually have a second encoding layer. It's a little more complex here because since, again, to create a sentence vector, I have to encode word vectors, right? And to create document vectors, I have to encode sentence vectors. So they're actually two separate steps. So essentially, the top box here shows you a sentence encoder. It takes IDs, word IDs that we just got, runs it through Embed, creates word vectors, runs it through the encode step, and creates a sentence vector, right? Now, Keras can allows you to return the whole sequence. So in case I said return sequences were true, it would take, assuming this sentence had 3 words in it, it would return me 3 vectors, a matrix of size, one of the dimensions was 3, right? But I can also say return sequence is false, which gives me the context vector. So it automatically contextifies the output, right? So that's how I get my sentence vector. And once I have this model, I embed it here into my document network, right? So each of these guys, I just embed the reference of this in here. And now I'm given a sequence of, this is essentially a sentence, a sequence of ints. And then I send it through my sentence model. It gives me a sentence vector. I encode that. It now gives me a document vector, right? And I take the document vector, send it through my predict step, and I get my label. Again, the code here is, so it's slightly more complex here. So I'm going to show you the code. I declare it in 2 steps. So here is my sentence vector. My sentence model. I have an embedding here, and I send this embedding through a bidirectional GRU, right? And so notice that I talked about the embed step, right? The embed step is already provided. The encode step is already basically this. It's already provided, right? And so I get this, and I get my output, which is a sentence vector. So none is the batch size here. And then I take my sentence vector, which I just said, sent encoder, right? I now embed it here in my document vector. So I have my inputs. My embedding is basically a time-distributed version of the sent encoder. So time distributed basically says on my second dimension of my input, I basically spread the sent encoder across all of the dimensions, right? So that's what I've done here. And as before, just like we had before, I take the output of this and I send it through this bidirectional GRU again, right? And so that is my hierarchical model. And this one takes, again, I train it over 10 epochs, and it gives me slightly better results, about 77%. All right, so the next step is basically adding the so the next step, I basically added the attention layer as well, right? So again, you won't see much difference. The sentence model now, the encoder emits matrix here, and then that matrix goes through an attend step, and that creates a sentence vector. Similarly, the document encoder also emits a document matrix, again gets through a attend step and creates a document vector. Everything else is the same. And so since I had built 3 different kinds of attention that uses matrices as the input, I tried running it through all 3, right? And the best result that I got was through the first one, about 82%. So here again, if you want to look at this, right? So remember I talked about return sequences, right? So now I want to emit a matrix, right? So I said return sequence equals true. So it's actually returning each time step down. And so I take the output of that, I send it through my attention layer here, and that's pretty much all the difference here. And similarly, I do the same thing here. I send it through my attention layer here. And this one gives me about 82.4%, right? And when I actually did so the other kinds of attention that I did, okay, let's see. So there's a slight difference here. So when okay, not this one either, sorry. So you remember I talked about sending a user-defined vector along with the matrix, right? So I did it here in this way. So I took my the sent encoder, the output, right? And then I created my sent vector, which is basically a global max pool of the sent encoder, right? So I just added a global max pool into this whole equation. This one actually did not perform as well as far as I remember. Oh no, this also is slightly less, 82.0. That was 82.4, right? And so that's basically my what I did with the document classification. And here are my results. You should basically ignore the red and the green one because those are just training and validation. My plotter was set up to do that. Essentially, you're looking at the test accuracy results, right? So, and as you can see, the bag of words is works the least, has the least performance, and as you use attention, you kind of go into the higher numbers. Our next document, the next example I have is a document similarity example. Again, just like we talked about before in the document classification, this is a hierarchical model where the sentence model is actually embedded in the document model. And I derived this data. So for the data, I basically took the test data for my 20 news groups. I created TF-IDF vectors from that, and then I did an all pairs on this 10,000. And then I took the top 95 percentile and over data as the positive, and the 0 to 5 percentile as the negative. And but unfortunately, the data was not really good. There's only a 0.02 difference in cosine similarity between the best and the worst. And so I tried without attention and with attention. So I'll just explain the diagram here for a bit. So if you look again, these are the word IDs. These are the, so for each word ID, I do an embed, I get a word vector. I take a sequence of word vectors, do an encode, I get a sentence matrix. If I want to use attention, otherwise I can get a sentence vector. And then I do an encode on that, and I get a sentence vector. Sorry, attend on that, and I get a sentence vector. And then I do an encode on a group of sentence vectors, and I get a document matrix. And I do this for my left-hand, both sentences for which I'm calculating the similarity. And then I attend on those two vectors, and I create a similarity or document similarity vector, right? And then I do a predict on that, and I predict whether it's similar or not similar. It's a binary thing. Unfortunately, the results that I got was not great. As you can see, it barely moves across the three different types. And so essentially what I did was, initially I tried it without attention. So without attention, I depended on the LSTMs to encode it for me. And then I just concatenated the two vectors, the document vectors, and I predicted on that. And then I did attention only for sentence encodings, like here. Sorry, here. And attention for both sentence encoding and, I'm sorry. So this attention is always there in both cases. And this is the one that I did with and without. So my theory here is that the data itself is so noisy that when I added attention, it actually it made it worse. I still have to look at it, but and I really wanted to basically show you how it works rather than kind of focusing on the results. So which is why it's is there. It's to look at the code. Here, let's look at the final one. Okay. If you look at the code, this is the sentence network. This should be very familiar by now. I mean, I've just reused the sentence network from before. And here, the document network is a document similarity network. So I create my left-hand document network, which creates an encoding. Basically, outputs a matrix here, right? A document matrix for the left-hand document. Another one that creates an output matrix for the right-hand document. And then this is an attention layer that concatenates the two. And this is where I use the batch normalization because my numbers were going too high and it was not learning anything. And then after this is just prediction, and that's how I got it. And okay, so this is basically the network. The next one I tried was slightly similar, but actually simpler to some extent. This is a sentence model, sentence similarity model. Once more, this is, it's got two kind of heads coming in. You're starting with word vectors, embedding, encoding, right? You're creating a sentence matrix, and now you create your sentence matrix on both sides, and then you do an attention on that, and you create your pair vector, right? And then you do a predict on it. This time it actually went worse, because with attention I actually got worse results. Once again, I mean, I wanted to basically, and it's possible that I have some bug in my attention layer as well. And I'm looking at it, I don't know yet. I tried to follow the paper, like word by word, but I think I'm right, but I don't know. So it does point to a bug, I guess. But I will look at it, and I haven't yet. So that's code-wise. This is much simpler than the previous one. Once again, you have the sentence encoder here, right? And then you have this full network, which you have the left-hand side and the right-hand side, and you send it through an attention, send it through batch normalization, then you basically run a predict on it, and that's what you get from here. And so I'm kind of reaching the end now, and so I'm going to summarize basically what we talked about. So essentially, this this is a 4-step recipe. What I liked about it is that it's a kind of principle. It's kind of a way to Lego blockize the whole process, right? So if you think of, it's kind of a higher level of abstraction, right? So if you work with Keras, it already gives you little layers that you can string together and make your network. This actually goes one step further. It actually looks at processes, and then you can string those together and make new networks, right? And each process is basically, you can think of it as a matrix transformation, right? So it takes a matrix of one dimension, creates another out of it, right? And it's all very well defined, and and so the embed step basically leverages the availability of many pre-trained embeddings. The encode step uses bidirectional LSTM, or nowadays you can also use CNN, but I didn't cover it here. Attention is of 3 main types: matrix to vector, with or without implicit context, matrix and vector to vector, and matrix to vector. Essentially, it computes a summary with respect to input or context. And the predict step converts the vector to a probability distribution, and then it creates a label for you, and that's pretty much it. I don't know what happened to this. Oh, okay, never mind. Yes, something is wrong here, but no. So here are my references. The first one is the actual blog post that led to this talk. The second one is, this is the blog post I read to understand how to build my hierarchical network, where I embedded one network into another. The third one is actually, I want to point it out because this is the place I thought that has the best explanation for attention. It talks, it shows you attention in terms of pictures, it shows you attention in terms of equations, and it's really good. I mean, you should, if you're interested in attention and implementing it, you should look at it. The rest of them are the 4 papers I kind of implemented for my 4 different flavors of attention. And that's pretty much it. The code is all here. The first is the GitHub, where you find all the code. The slides are up already. That's here. My email is this, and my Twitter handle is this. So in case you guys want to get in touch with me later. And also, a co-author and I, an ex-colleague and I, we wrote a book on Keras. And the publisher, basically, he was kind enough to give me a discount code. So in case you guys want, this is, there are 3 basic books on Keras right now. One written by the author of Keras, so maybe that's the book is the best, but, yeah. But, this is there. I mean, this, yeah. Okay, I'm done. Thank you.
Thank you so much.